Yeah. Good morning. So we were done in the last class about understanding another important metric called static margin. Like you have your understeer gradient, which is the metric obtained from steady state equation, fundamental governing equation of steady state motion. You are able to derive the expression, and that you could see the steering angle required is depending upon what is called an understeer gradient value. Right, so that was considered to be a metric, and we could use that metric to compare the vehicle handling characteristics of different vehicles in a steady state motion. Is what we have learned earlier. And in last class, we got to introduce with another metric called static margin. So static margin is the point in a vehicle on a line called neutral steer line, where the neutral steer line is the locus of neutral steer point. So that neutral steer point is the point in a vehicle where the side force act at that point will not produce any steady state yaw motion. Is what is how you define what is that neutral steer point. The location of neutral steer point from CG of your vehicle normalized by dividing by wheelbase is what is defining static margin. That's what we have seen in the last class, and we could derive an expression of the distance of your neutral steer point from the CG location in the earlier in the last class. And also we have looked at essentially in another rule called definition called Wolle's definition for to define vehicle tendency. So the Wolle's definition basically from steady state understeer gradient. That is defined as the difference in front and rear tire compliances. So if we have your front compliance of the vehicle is more than that of the rear compliance, the vehicle would behave as an understeer effect. If it is other way around, it is going to be behaving like an oversteered vehicle. If your front tire compliance and the rear axle tire compliance are same, then the vehicle is of neutral steer tendency vehicle. Is what is the definition from Wolle? So it's called Wolle's definition. So this is essentially in the last class we have looked at. And we are going to get in today's class an important part of our lateral dynamics, where we are going to look at our bicycle model added with the suspension into it, right? So far the bicycle model we have used to study the response of the vehicle, particularly in steady state motion. We have derived transfer function, we have derived steady state gains, we have interpreted their physical insights and so on. So that was with the primary assumption of a bicycle model where front axles are collapsed and treated as one single wheel of double the cornering stiffness. Similarly, the rear axle collapsed and the rear axle is treated to be one single wheel. And the entire weight of the vehicle is considered in your bicycle model. There is no discretization of your vehicle mass as an unsprung and sprung mass. That is essentially accounting the assumption that suspension part in the vehicle is removed and it is treated to be one rigid vehicle. So what was that effect in your motion? Even in steady state motion, there won't be any load transfer when you do a hard cornering from inner side to outer side because you do not consider suspension. But you cannot do that all the time, right? So you have to account that. So when you account the suspension and you discretize your vehicle mass, sprung mass and unsprung mass, what would happen is the vehicle will roll during hard cornering, and then suspension do have an effect on cornering. So today's class we are going to learn the role of suspension on vehicle roll and how it is going to influence your understeer gradient is what is today's class lecture that I am going to teach you. So let me share my board. So hope you are able to see this board, and this is lecture number 27. And today's date is 15/10/2021. So what is that today you are going to study is suspension effect on cornering. suspension effects on cornering. So what is essentially we are going to study is the role of suspension in vehicle roll. Look at this roll and this roll, right? Vehicle roll that influence understeer gradient, right? So this is what we are going to look at in today's class. Let's just to recapitulate or understand what is bicycle model. In bicycle model, the suspension is not considered. When it is not considered, there is no roll effect. Hence no roll in the vehicle, model. So we looked at the steady state motion of the bicycle model in cornering from the fundamental equation delta F equals L by R plus KUS into U squared by RG, where we define KUS by tire compliance. Right. So this is what we have so far looked at in bicycle model, particularly for steady state motion, right? For steady state motion. This is for steady state motion. This is your fundamental governing equation. And what is this? KUS is called the understeer gradient. Understeer gradient, or it's called understeer coefficient. So it's primarily depends upon tire compliance alone. That's what is defined by Wolle's definition, right? So now today's class we are going to look at additionally. Why? Because in real time the vehicle design aspect is going to be influencing this understeer gradient, even that is driven at steady state motion. So that is where we have witnessed that from handling diagram, or there are handling tests for handling characteristic prediction, constant radius test, constant speed test, or constant steer angle test, and so on, where we were able to look at the requirement of steering angle as function of lateral acceleration, and we were able to define your understeer gradient by slope of the curve. And we could witness in our test case studies that an initial understeer tendency vehicle would change into an oversteer vehicle at some critical speed. And that is what we have witnessed. And that would happen in your real-time vehicle. So we can witness such thing by conducting real tests, or we have sophisticated softwares like CarSim software, where you have a vehicle template, all subsystems are assembled. So you would be defining every system under real vehicle parameters. And then you would do this test virtually, and you would see that when you do such test, and then the plots that we have seen, and you can define this KUS is no more constant for the given vehicle. That would change according to the design and operating condition of the vehicle. So if we keep that in mind, now as in our bicycle model, we are going to include now the suspension. We should see that how this KUS is going to change. That's what is today's class that we are going to learn. And for that, let us first understand importantly a model description for today's class, right? I'm going to describe the model required for today's class. So that's a half car model. So half car model means you can have a half car either by slicing your vehicle by symmetry plane XZ, or you can slice a vehicle by YZ plane through CG. So I'm going to take the second case, and my vehicle is defined like this. So I will have my half car where this represent the axle. Where if you look at this axle, the front axle and rear axle wheels are collapsed and they have taken together. And similarly, the front and rear axle taken together like that. It's not like a bicycle model, right? So you see this axle in your vehicle. And you also have suspension in the front and suspension in the rear. So the front suspension of left side and right side will be considered along with the rear suspension of front, left and right side. So you would have one side equivalent suspension spring and the other side also an equivalent suspension spring. That would be represented by these springs. So if you look at, this is my left side suspension spring and this is my equivalent right side suspension spring, right? And I have my vehicle. I'm exaggerating this diagram. I'm having my vehicle in this way, and this is CG of my vehicle, right? This is CG of my vehicle. So how this vehicle has been taken? This vehicle has been taken in this fashion. So I have my vehicle considered for the time being a van type of vehicle. Why? Because in that I would have now the half car model is taken something with this. So when I cut and remove this portion and view, how does it appear is what is this portion, and the wheels are taken together, right and left side wheels represent this and this, right? So if my vehicle is going to turn in this direction now, so this is my inner side, this is outer side of my vehicle. And the springs are shown exaggerated. It is exaggerated like that. So you can see that this is done is to discretize your vehicle mass as sprung mass. So this is your sprung mass. And this portion is your unsprung mass. Unsprung mass now. So now you have to define an important term. As it is going to take a turn, the load from your inner side to outer side would be transferred, and that load transfer would make this sprung mass to roll relative to this unsprung mass. And roll will take place at what point? It would take place at the point called roll center. So this is roll center, RC. So what does RC refer to? Roll center. Right, so now if I look at my free body diagram, I would have my weight sitting here, and I will have here a load and here. So this is a F is at naught, F is at I. So this is the free body diagram. Vehicle goes straight coming to us. So I just remove this portion and view from here. So I view from here, removing this. What is this vehicle now model I'm describing? So when I describe this vehicle model now, as it is going to take a turn in this sense, this is the inner side and outer side, but just before the turn, you see the weight would be acting down, and then you will have this is the force equation. And of course, you'll have in a longitudinal direction other forces here. I'm not showing that for the purpose of today's context. What are the required forces? This is not its complete free body diagram. If that is so, I should say here what is my tractive force? What is my tractive force in this? And then there is rolling resistant force, and there can be an aerodynamic force. So many things are there. But I'm just drawing this picture to the context of today's study alone, right? Okay, so if that is so, this is the scenario. So what would happen when it is taking a roll? When it is taking a turn, the body rolls. So I'm just going to draw with smaller exaggerated way. So as the load going to go on this side, there is more dynamic deflection of the tire here compared to that of this side. But this side is not losing its contact. It would happen when this W goes out of this wheel. or just coming above this wheel. But the smaller roll only we are considering. We are having steady state motion and it is having a hard cornering and there is small roll. When you consider a small roll of your sprung mass, that is what is the diagram I'm going to draw here now. So I would have my axle, outer axle, and then inner axle slightly more than this dimension. And there is small rotation of that is not, that's neglected. There is a roll of your unsprung mass as well, right? So the small angle here that you can neglect it. And I have here, of course, this RC point and my spring this side and this side spring, because the roll is outer side. So the spring would have gone somewhere here and the vehicle has changed the orientation like this. So this is now initially, this is my vertical reference plane. And now with respect to this roll center, let us define what is roll center. This would have gone here. The CG initially located here would have gone here now. And this angle is what is roll angle, phi. That means this angle here is what is roll angle. So what is phi? It is roll angle. So what is the motion that I'm going to consider in our study is steady state motion again. When I consider steady state motion, now what are the free body diagram changes here? So I would have here, of course, I have my F is at not slightly greater than this, so I may have smaller length here compared to this. This F is at I. And as this is doing a cornering, it is required that your tires to develop your lateral force, that is Fy naught, and here this is Fy I. And see what is roll center now. Let's define now what is roll center. So roll center is something that you can analogously look at. How did you look at neutral steer point to define your static margin? In neutral steer point, you had your side force acting will not produce no steady state motion, right? No steady state yaw motion is what is defining static margin. Similar way, roll center is the point when your side force is acting at roll center will not produce no roll. So roll center is the point, when side force will not produce roll in the vehicle. Right? Roll center is the point when side force act at that point. Act at that point will not produce any. So if my resultant side force which is acting at my roll center. So roll center, how does it appear for the vehicle? Just let me put. So if this is my front axle, there will be a height from the ground. And there will be a height from the ground. And this would be the roll axis. This is the roll axis. I take here, so the point here is what is roll center here. The roll axis is not horizontal, it is at an angle, smaller angle, epsilon given, right? So the front roll center in the axis above the axle would be at a height HF. And here it is at a height HR. So now in my diagram, how do I look at my geometry dimensions? So if you look at this contact point to contact point, this distance is what is called a track or tread, small t. And the equivalent suspension spring on one side and the other side, considering this van and it is of solid axle suspension in both sides, so the separation distance is given by small s. And this spring rate, the vertical stiffness of this spring, equivalent spring, front and rear put together is Ks, and here is the same Ks. Right? So instead of this, if you take a passenger car and you see front axle or independent suspension, then you would take instead of S, T there straight away and you proceed. Right? But for the easiness of our derivation, I'm just considering this van type vehicle, and the front and rear suspensions represented here is separated by distance S. And my roll center is located from the ground at a height HRC. And from that is this. So this height is HRC. And from here to CG is located from roll center is at a distance H1. We know the H is small letter H is what is the height of my CG from the ground. So roll center is measured from ground. CG is measured from ground by HCRC and H respectively, whereas the CG location of a vehicle from roll center is by height H1, because the sprung mass rolls about the roll center. So roll center is because the vehicle body would roll about this axis. In this diagram, it will roll about this point, right? Okay, so this is all what is called a model description. What you have seen here is model description, model description. Right, so still here the forces are missing. You would ask that. What are the forces? So here I have this, and this Fy, whatever is generated with the tire, what is manifesting the required centripetal acceleration during the turn, and that would act to the right in this direction because your vehicle is taking a turn in this direction. And you see that the roll in this side, and the centripetal acceleration would be always towards the center of curvature of the curve of this bar. So in this direction. So D'Alembert's force would act in which direction? It would be acting in this direction. So that is what is the D'Alembert's force. That would be W U squared by RG. And as it is steady state motion, you know Fy is equal to MRU is the only equation in this. Where MRU is nothing but centripetal force, or in this diagram what I represented is D'Alembert's force or centrifugal force. It is in this direction for dynamic equilibrium. So this diagram is drawn in this plane for dynamic equilibrium in this which plane? In YZ plane. So this is YZ plane, right? So this line, what is drawn as YZ plane. YZ plane, right? Yeah. And of course, here you have this weight acting, but this weight also is acting. It is exaggerated. This angle is exaggerated. This is appearing more. Almost it is like 15-20 degrees are drawn now, but it is hardly of some 2-3 degrees. And smaller angle, this W passes through RC. So in your Gillespie textbook, this force is not represented. Correct? Okay. So this is that dynamic equilibrium in which plane? YZ plane of our Haftar model for the lateral equilibrium, right? Okay. So any doubts at this point of time to understand this model description? Anybody has got any doubt? Do you have any doubts? Jose?
No, sir. No, sir.
No doubt. Okay. So let's proceed. So how this force here manifested, you know, how this force has come here. That's what is the beauty that you have learned in your engineering mechanics course, equivalent force coupled system. So RC is the point. You can also refer roll center is the point through which this lateral force developed at the tie rod interaction get transferred to the sprung mass CG. That is what you should say RC. So if that is the statement, how did you understand that? So for that, let's just look at this diagram now. How nicely it is getting transferred. I'm just drawing this ground. This is ground. And in this, I have now Fy in this direction. This is my Fy. So what is Fy? It is Fy naught plus Fyi. Fy naught plus Fyi. So I have here Fy naught and Fyi. If I add, that is Fy here. So that is acting in this direction as the turn is in this way, going for the vehicle. I'm not drawing the vehicle here. And this point is my roll center. This point is my roll center. And this point is my CG, right? So now see, this Fy can be shifted here, you know that, and then can be cancelled here. So by shifting this, you see this and this form a couple. And this couple is independent of roll of your vehicle body. It is an instantaneous couple as this force get transferred there, right? And it is independent of the roll of your vehicle body. CG is not rotating. So this force, when I have to transfer to sprung mass, it passes through RC. So this would make a momentary rotation. This couple act on axle now would make your axle to roll. But that is an instantaneous action because it's steady state motion, and then it would be keep going, right? That's very smaller angle compared to the vehicle roll. And this is what is one couple form. Then here again Fy is there. This Fy would be again transferring Fy, and then that is cancelled Fy. So now again look at this Fy and this Fy. That is what is your couple, another couple. So this forms a couple. So what is this couple moment? It is H1 into Fy. What is this couple? It is HRC into Fy. So HRC into Fy is this couple, and Fy into H1 is this couple. So this force is what is now your required centripetal force in a free body diagram. So these all are equal to this Fy is replaced by MRU in your diagram. That's all. So these two couples are now, how is it balanced? So this couple is what is inducing the roll in your vehicle, and the roll is counteracted by the roll stiffness of the spring. The roll stiffness of the spring. Because there is restoring couple. This Fy into H1 is a couple that causes the body roll, but that is not keep on rolling it. It has been restrained by another couple, that is what is given by roll stiffness of your suspension times the roll angle. So let me just write down the important equations now below from this described model, and we will be able to understand this physics nicely, right? So the very first equation is, I know my total lateral force required to get generated for taking a turn like this is Fy naught plus Fyi. So that's my equation 1. And my second equation is Fy into H1. Fy into H1. This one would be now, because the second one is what is the roll of sprung mass, that would be equal to K phi into phi. So where here K phi is what is called roll stiffness of the suspension. And what is phi is roll angle. So you know the unit of roll stiffness. It is Newton meter per degree angle. Multiply by angle, you get Newton meter. So that is what is the couple, and that is restoring couple, and that would be equated by Fy into H1. So this is my second equation. So what is my third equation? My third equation to get, I am going to take moment of these forces about RC. Moment of these forces about RC. In this W, I would consider that passes through this because of smaller angle, I neglect the moment by this W. So I would have four forces, 1, 2, and then and then these two summation Fy, right? And that is this two put together Fy, that's my 3, and then this force here, what is there? Is what is my Fy. So this is Fy, right? That is what is equal to this. So this is my fourth force. So when I take moment about now RC in this diagram, I get my third equation. So let me just put that equation now here. So what is my equation? So minus Fz naught, take this, and here clockwise moment is what is going to be negative, right? Because this is a turn and your forward direction, the moment would be positive in counterclockwise sense. So I would take that here according to that convention. So the moment of all forces about RC, considering counterclockwise positive equating to 0, I'd have this third equation, that is this force into T by 2. Then plus F is at I, that is on this side normal, into T by 2. And then Fy naught plus Fyi, addition is Fy, into that about RC, it is counterclockwise. So plus Fy into HRC. Then plus I have Fy at CG, so Fy into H1. So Fy into H1. So my centrifugal force, which is Fy here, into H1, I'm just taking it. So that is when it is straight and it is taking a turn, slightly it's rolling. Then I just exaggerated that and I take the moment. So this Fy into H1, counterclockwise moment, F is at I into T by 2, and Fy into HRC, minus F is at naught into T by 2, that's minus clockwise. So this is all equal to 0, and this W into this is not considered in this, and instead we will look at now the roll moment along with that, considering the whole body, considering the roll axis. At that time we will consider that. In this diagram, the moment is not considered because this angle is very small angle, and this distance is h1 sine phi, and sine phi here is going to be phi itself very small, and that is neglected. That momentum is neglected. That's why in Gillespie textbook, this W is not shown in the diagram itself, right? And you have this, and this essentially going to give you two mechanism of load transfer. That's what you'll understand. So this all sum of the moments is equal to 0 would yield my equation. So this is equation number 3. Equating to 0 is what is equation number 3. And I would rewrite this equation now as this. I will take now this has got F is at I. So what is the change in normal load is what I am interested in. So if I take this negative term on the other side of the equation, and it is F is at naught minus F is at I. This I take it on the other side, F is at I. And the 2 by T by 2 was there, that I will bring it in this side, and that's going to be now written like that, 2 Fy HRC by T plus 2 Fy H1 by T. So this is that equation 3 is rewritten now, just manipulated on both sides, and this is what is delta F is at. Change in normal load in my model. And here I have the first term is 2 Fy HRC by T. And the second term, I'm going to replace this Fy H1 by equation 2. So that's going to be 2 K phi into phi by T. And this is my fourth equation. This is my fourth equation. So here, if you look at the two terms, are referring to two important mechanism of load transfer or the vehicle roll. The first term here is due to lateral load transfer. Correct. The first one is what is due to lateral load transfer due to cornering force. lateral load transfer due to cornering force. Right. So this portion is due to that, due to cornering force, on where it is realized in your axle. Lateral load transfer due to cornering force in axle. In the axle. So the axle rolls, but it is an instantaneous effect. So this is not that important factor. But you look at this one, this is referring to lateral load transfer due to vehicle roll. This is due to cornering force Fy. So this Fy is at the contact patch, and this is lateral load transfer due to vehicle roll. You see the explicit appearance of roll and the roll stiffness of your vehicle, right? So here I just want to relate this roll stiffness of the vehicle with the spring rate of the suspension, right? And I leave it to you to do as a homework. It's a simple explanation. So this K phi would be given by half into Ks into S square. You can prove this simply. I leave it to you. Otherwise, later on we will see. Right? Want of time, I just don't do it that now. So this is your roll stiffness. Stiffness relationship with the vertical stiffness of the spring. This is vertical stiffness of the spring. Vertical stiffness of the spring. And what is the S here is the separation distance of your right and left side equivalent spring rates or the equivalent springs of the suspension. So this is K phi. So K phi into phi here, your change in normal is because of lateral load transfer, that's because of vehicle roll, right? Okay. So now what is that I'm going to do is I'm going to consider the important understanding of what is roll moment distribution. That you need to understand. So why do I say now roll moment distribution is because see this is whatever this vehicle model what we have done all correct to know what are the two terms or what causes this change in normal load here. So if this delta FZ is going to be delta FZ is what is change in normal, right? So if that is equal to 0, what does that means? That's equal to 0. What does that means? It is going straight. So FZ naught is equal to FZI. That's the meaning. When that is going to be 2 times FZ, 2 times FZ. So here and here it is there. So you see in this diagram, the length is reduced. When this become disappearing, that is the point of tipping of your entire vehicle about this outer side. At that time, you would see where delta FZ would be delta FZ would be what? It is going to be doubled here. So 2 times FZ naught, it becomes like that, right? So this side, whatever is there, entirely it goes. So to understand this, you need to consider the whole vehicle for that. So before that, let us understand the roll moment distribution in the front and rear axle. Going to decide on your vehicle tendency. And for that, let us look at now the variation. See, so far what we have considered in our bicycle model, we have considered linear tire model. So what I mean by linear tire model, I look at my Fy as function of slip angle, and that would vary like this. But I have taken the stiffness of my tire by this slope from this point, that's C alpha. So the C alpha of a tire is considered to be constant, and you define this C alpha like this. C alpha is limit alpha tends to 0 dfy by d alpha is what is giving you this, right? That is how you have defined the C alpha. And your Fy is simply given by this constant C alpha times alpha. This is what you have considered. This is linear model. And also importantly, whenever you consider this, you make another important angle, which is gamma, camber angle. 0. So camber angle 0. And then your slope of this variation of Fy as function of alpha, if you plot, limit alpha tends to 0, dfy by d alpha defines your cornering stiffness. And that cornering stiffness value constant was taken. That is what is the linear model. That is in bicycle model. But in real time, this Fy is function of normal load. This Fy is function of normal load. Function of Fz. Fz. So how does it vary? Let us just look at it. So if I take Fy on vertical axis and Fz on horizontal axis. So look at here, it's normal load. In this graph, it is slip angle, right? The variation of this Fy is not linear. It is going to be non-linear, something like this. This way it will vary. Going to vary like that. So what does that you understand from this? So if I take a particular value of normal load, say 800 pounds of a case study vehicle available in the textbook. If this is the normal load in a particular tire wheel, and then that can produce correspondingly in the possible lateral force 760 pounds. 760 pounds that would produce, right? At a particular slip angle, slip angle say 5 degrees. So this is the case study presented where they have plotted the variation of Fy as function of Fz. And you see for a given tire wheel, single tire wheel assembly, if this is a normal load and that would create this much, right? If I consider now the two wheels of a vehicle and one side and this and the other side here, the value of the normal in that same tire, if I consider two wheels in an axle, in a hard cornering, this would typically, the inner one would typically reduce to 400 pounds and the outer one would increase by 1200 pounds. Whatever is reduced in the inner side, that is Fzi, and this is Fz not, like that. So if that is so, if I look at my values here now, in a particular tire, I would have this value, average value, right? Such that I will have this much only. So you see here, what is that it can develop in a hard cornering is not 760, it is going to be 680 pounds only. 680 pounds. So which is not sufficient for to generate the required cornering force or centripetal acceleration. So in such cases, you see the tire, pneumatic tire, which is non-linear and depending on the normal load, would have capability that it would increase the slip angle. So you would have this curve would be increasing. So the slip angle would have to increase essentially to maintain that. So this is what would happen in your tire when you consider the tire to be a non-linear tire model. So far we have not considered bicycle model like that, right? So you understand this. So why this explanation here is what is happening in your tire rod interaction is the slip angle would get increased as it is in a hard cornering. The load transfer, lateral load transfer would not generate the required 760 pounds. Instead, it would require, it would only generate this, and that would enforce on the tire to go for an additional slip angle increase. That would essentially increase your Fy like that. So This is what is the behavior. So in such cases, this is not sufficient to say what would be my roll moment distribution. So I should account, this is for one axle. Similarly, what is for rear axle? So roll moment distribution in front axle is how much and the rear axle is how much. If I know, then I would be able to talk on my vehicle tendency, right? So what is happening here is you understand the tire behavior. So slip angle increases. If this slip angle increase happens to be on the front axle tire wheel, so what will happen? You would have more Fi in the front axle and the front axle will plow out of your motion. So you are taking a turn in this side, but rather doing it, your slip angle would be always like that. You know, bicycle model you've seen, right? If you are steering here, your wheel, so this is your delta F, your slip angle would be measured from here in this direction. Your slip angle is this alpha F. So if this slip angle in the front axle increases, what would happen is the roll moment distribution in the front axle would be more than that of the rear axle, and that would make your vehicle to understeer effect. If the slip angle increase, load transfer such that happens in the rear wheel, what will happen? The slip angle more increase in the rear wheel, it would pronounce the vehicle to behave as an oversteered vehicle. But we can't explicitly say that because just because of increase in slip angle alone, we cannot say. That's what we have understood. The role of your vehicle to be accounted. So to account the entire role of the vehicle and looking at the distribution of roll moment in the front axle and the rear axle, I have to consider the entire vehicle model. So I'm going to consider now a full vehicle model and develop some equation. So another 5 minutes I would complete description of this and then we will do smaller calculation in the next class. Right. So what am I going to do is now I'm going to represent my vehicle full model. So I have it here. This is my front axle wheels and this is my ground plane, the contact with the ground. And I draw this ground line. And again here, my rear axle. So I have my wheel assembly here. Rear wheel. Right. So this is my full vehicle model. And now I have my front axle roll center somewhere here. Rear axle load center from here, from the ground. So this line is what? This line is on a ground. This is on a ground line. And this height is now HR, HF it is front and HR here. So the roll center at the rear is slightly more than that of the roll center in the front. And this line is what is called a roll axis now. So this is roll axis. And this roll axis is inclined because of this, and that angle is epsilon, right? So now your CG is somewhere located from here at a point somewhere here. This is your CG location. And here your weight initially acting as this is taking a turn like that, the roll will be outward and this would have the roll. I'm just exaggerating this diagram. So this is my roll angle phi. And I have my CG transferred here. And that would have my W, see, and my centrifugal force. It is M V squared by R, you say. So W by G. So in terms of W to right, I have this. So this is my centrifugal force for the equilibrium. Right. So now what is this height? So this height here is H1. This height is here H1. That is distance from RC to CG location is H1. Right. So this is my model now. So I would consider here the role of your vehicle is same about this roll axis. So I have my front suspension, I have my rear suspension. There is a roll stiffness of front suspension, rear suspension. But the role of your vehicle body is same. So you would have your total roll now as like this. So we had written how many equations for 6 equations, I suppose. We have written 5 equation, and let's write now my 6th equation here. The 6th equation. So 6th equation, how do I write? Is taking moment, right? So the roll moment M5 would be taking this side as positive. This is positive. So now what is that I have here? This W into this distance. So what is that distance? This distance. So this distance would be H1 sine phi. So this is H1 sine phi. And this distance would be from here. This distance would be H1 cos phi, right? So let me write now my equation here is W into H1 cos sine phi. Sine phi is what is moment by this H1 sine phi plus W u squared by Rg into H1 cos phi. So this is now moment about this point. So I have about this axis, roll axis. So this is moment about this roll is about the roll axis. This is about roll axis, roll axis. But I wanted to have it with respect to longitudinal axis of my vehicle. That is horizontal. That's parallel to the ground axis. So you have to multiply by cos psi. Cos psi. So why the cos component is because the dot product. So I want to have my moment vector, which is this, along the roll axis that has to be projected along this. So the projection would take a dot product. So this cos I comes here. And you have now, this term is what is your equation number 6. So this is your roll moment. But this roll moment is, that is equal to this M phi, what we have would be equal to M phi F, front axle roll distribution plus M phi R, M phi F plus M phi R, and that would be equal to K phi F. So the roll stiffness of my front suspension value into phi plus K phi R into phi. So this phi is same for a vehicle. So this is what is equal, and this is my equation 7. Right? So now equation 6 and 7 can be combined, and I can get what is my roll moment. Correct. So this is equation 7. So let the equation 6, let me look at it like this. So in this, I want to write what is for phi. So let's considering phi psi are very small. You have sine phi equals phi and cos phi equal cos psi equals 1. You know that. So this equation 6 would become now what? M phi equals WH1 phi plus W u squared by Rg into H1. And this is also 1. So this is become now. So now I am going to take this one along with this. Right? This is in this, if I take my WH1 is common, WH1, if I take it out, what is that I have? Is here U squared by Rg term. That's from the second one and plus 5. That's my equation 8. That's my equation 8. Right. So now look at, I have my M phi given by equation 8. I also have my M phi given by equation 7. So from 7 and 8, I can rewrite this as K phi F plus K phi R into phi is what is equal to WH1 into U squared by Rg plus phi. Right? That's my equation 9. That's my equation 9. So now, why do I do that? I want to get what is my roll angle. So roll angle here I have in this term as well as in this term. So if I have to get my roll angle, I'll take this term on this side and then bring that other term again back here. So I can rewrite from 9 equation. Roll angle 5 would be WH1 5 would go on that side and 5 I get taken common and then again bring the terms here down. That would result in WH1 into U square. U square by Rg divided by K phi F plus K phi R minus WH1. So this is what is my equation number 10, gives me what is the roll angle. So during steady state cornering, considering suspension into my vehicle model, and I see now what would be my roll angle that is dictated now in terms of vehicle total weight, the geometry, and then roll stiffness of the suspension, and of course forward speed, steady state speed, and the rolling radius, or you can say this is lateral acceleration. So these all are dictating what is your roll. So now if you look at in this, other than this term, rest of the terms are constant for the given vehicle. So I would get what is called the roll rate. The word rate should not be misunderstood as a function of time varying. In this case, it is variable as lateral acceleration. In automotive industry, roll rate is defined as roll angle derivative as function of lateral acceleration. So that would be, so this is what is your AY, normalized AY. So U squared by R is AY in terms of G, right? Because it is divided by G. So if that is what is taken here, AY is in terms of G, AY by G, or AY in G units if I write. If I differentiate, what is that I get is WH1 by K5 F plus K5R minus WH1. So this is equation number 11 and called roll rate, very important. These definitions all would be asked in an interview or in your examination, right? So what is the typical value of this roll rate for cars? The roll rate would be given 3 to 7 degrees per G. So if you're getting 0.3 G is AY, then what is your roll angle? How do you get? How do you get that? Then your roll is equal to roll rate. This whatever that you have, dou phi by dou AY multiplied by this 0.3 times G. If you do, you get that angle, and that's what is your roll angle. So that's how it is calculated. So we have defined till here roll and roll rate, and we have another some 10 equations to write. We will do that in the next class. I'll stop at this point of time. Of course, what is the objective here is to understand the roll moment distribution. So if I have my roll moment in the front axle, that is M phi F is more than that of the rear axle, then the vehicle tendency is understeer tendency. If M phi R is greater than M phi F, then the vehicle tendency is oversteer tendency. If the roll moment distribution is same in both, then it is neutral steer tendency. That is how you can say the effect of roll on your vehicle, right? So when roll moment distribution more than that of the rear, it is understeer you are saying. That means already the vehicle is understeer because of your tire compliance. This get added and then vehicle become more understeer. That is what. So this roll moment distribution, the vehicle roll contribution to understeer gradient is yet we have not derived. We are in the process of deriving. That we will complete in the next class. But you understand that significance or the need of roll moment distribution is because your real vehicles do have roll stiffness of their suspension, whereas the bicycle model doesn't account the suspension. However, that model was good, quite good enough model for steady state motion and then understeer, steady state understeer gradient and so on. We have looked at it, right? So with that note, I'll stop today's class at this point of time. and then again we will look at in the next class. So before that, I just want to say one more point. You also have now, so if your vehicle is behaving oversteered vehicle, you want to make your vehicle to behave as an understeered vehicle. What do you do is something called an anti-roll bar, or it's called roll stabilizers. So you would put that roll stabilizers in the front axle. So the stiffness of the roll stabilizer should have to get added with the roll stiffness of the front suspension, and then the vehicle would behave as an understeered vehicle. Or you want to have your roll more on the rear, you have to go similar way. Put your roll stabilizer on the rear side, and you get your more stiffness there. So the roll moment distribution is smaller compared to that of the front, and that can take you to oversteer. So the auxiliary stabilizers or roll stabilizers are something which are addition to the suspension in vehicle design that you can see. So with that note, I stop today's class. And in the next class, we will look at the tire as a nonlinear tire model. As function of F is that we'll define your F, C alpha F, and then count the nonlinear tire model along with this roll moment distribution, and then trying to get observe how that understeer gradient would change is what is the starting point for next lecture on Monday morning. So do you have any doubts? You can ask. Otherwise, I will stop recording.